In step 1, a pool ball is added to a pulley system, causing an imbalance in force. This causes the heavier side of the pulley to slide down and the lighter side to be pulled up. This applies most to Newton's first and third law, which state that an object at rest stays at rest, and every action has an opposite reaction. To elaborate, the pulley system began at rest. When the pool ball was added, the pulley then reacted, falling onto the button below it as a result of its force.
Step 2, the falling pulley hits a button that, when pressed, causes horizontal motion. Conservation of energy is demonstrated when the pulley hits the button. As it falls down, the potential energy it had while suspended midair, or mgh, converts completely into kinetic energy. Newton's second law is also demonstrated. According to the law, the sum of forces equals mass times acceleration. With the added pool ball, the pulley weighed more, causing its mass value to increase and thus its net force to also increase. This force was large enough to hit the button successfully.
In step 3, the horizontal motion in the previous step accelerates a wooden ball. Conservation of momentum, which states that m1 delta v1 equals negative m2 delta v2, is demonstrated here. The mass of the red contraption is less than that of the wooden ball, so the velocity that is transferred to the wooden ball is smaller. However, it is still enough to push the wooden ball down the ramp.
In step 4, the wooden ball continues its motion in the horizontal direction and speeds up as a result of the declined plane. This step can be related to the conservation of energy. The potential energy the ball had before moving down the ramp is now converted to kinetic energy.
In step 5, the wooden ball strikes the first suspended ball in a Newton's cradle. Conservation of energy can be seen here. Energy is transferred through each ball and exits the last ball with the same force the first was struck with. Newton's third law also applies here. There is an equal and opposite force put on each ball in the series. The last ball in the row then continues the motion in the horizontal direction.
In step 6, the force on the last ball in the Newton's cradle causes the ball to accelerate and knock into the glue stick. Newton's first, second, and third law are most evident here. The glue stick begins at rest, but due to the force applied to the Newton's cradle, the balls accelerate into it. As a reaction, the glue stick is knocked into motion.
In step 7, the glue stick, given its narrow base, was destabilized by the Newton's cradle. As a result, it toppled over the edge. In this step, the glue stick's potential energy is converted into kinetic energy as it falls down the ramp.
In step 8, the glue stick, now with more kinetic energy, hits a lighter. This is the first in the series of dominoes. The lighter knocks over a guitar tuner before hitting a series of disc cases. In the series of dominoes, smaller objects knock over bigger objects. This is due to the fact that the potential energy of the falling objects is converted into more kinetic energy. This does greater work.
In step 9, the result of the dominoes is a transfer of energy that bumps a tiny wooden rocking chair holding a toy tire. Newton's third law is demonstrated here, as the rocking chair has an equal and opposite reaction to the dominoes.
In step 10, the movement in the rocking chair causes the tire to roll off of it and accelerate forward. Newton's second law causes acceleration in the tire. The forward applied force is equal to the mass times the acceleration.
In step 11, the rolling tire exerts enough force on the weighted cup to knock it over the edge of the billiards table. Conservation of energy is shown here. From the top of the billiards table, the cup has a potential energy equal to mgh. When it is knocked off, the potential energy is then converted into kinetic energy.
In step 12, the cup lands on a plastic lid and slides into another disc case. Conservation of energy can be seen here. The kinetic energy of the cup sliding down the lid is transferred to the previously stationary disc case.
In step 13, the disc case collides with a pool ball and causes it to roll on its track. This showcases conservation of momentum. Since the disc case weighs less than the pool ball, the velocity that is traded is less than that of the case's initial velocity. This causes the pool ball to roll at a slow enough speed to maintain its course on the track.
In step 14, the rolling pool ball bumps into a pail holding a rubber ball. This disturbs a game case that is elevated in one corner. This showcases Newton's second law. The force exerted on the flat disc case is directed slightly downwards towards the ramp due to its elevation in the opposite corner.
Number 15.
Due to the slanted position of the case, the pool ball then moves toward the ramp. According to Newton's second law, the force exerted on the pool ball due to the case's movement underneath it causes it to accelerate toward the ramp.
In step 16, the pool ball rolls down the ramp, garnering more energy. Conservation of energy applies here. The potential energy of the pool ball is converted to kinetic energy. It then accelerates down the ramp. In step 17, finally, the energy gained by the pool ball is sufficient enough to press the button. This demonstrates Newton's second law. The mass and acceleration of the pool ball creates enough force to push the button down and complete the process.